Breaking the wall of molecular movies. Rebecca Boll, Deutsches Elektronensynchrotron, Hamburg.
Hello and welcome everyone. I would like to ask you, what do you think is the difference between a molecule and a horse? Well, I'm guessing that probably you can come up with many of those, but the most fundamental one for us is actually this. So what you see here is the first movie that was ever taken, and it revealed that actually all 4 feet of a galloping horse can be off the ground at the same time, which was not known before. However, today, we regularly watch 3D movies on a day-to-day basis, but no one has succeeded up to now to record a movie of just a single molecule. And this is what we're trying to do. So we're wanting to see individual atoms of a molecule move in time and space. We're wanting to see how chemical bonds form and break during a reaction. But in contrast to a horse, a molecule is about 1 million times smaller and it moves about 1 billion times faster. So you can imagine that this is not all that easy. Let me try to explain to you what we think could be a way of doing this. So what we're using is an ultra-short pulse of X-rays, which releases an electron from the molecule. And when this photoelectron leaves the molecule, and we detect it on a screen, basically, it forms such an holographic image. And in certain cases, from this image, we can directly reconstruct the 3-dimensional structure of the molecule. What you see down there is the 6 dots of the carbon atoms in the molecule up there, reconstructed from the electron image you see on the left. And in the experiment, what we did, we used such a free electron laser to do that. It's a device that's actually more than 1 kilometer long and it's located in Stanford in California. So when we could establish this technique to record not just the first movie frame, it's supposed to say down there, but to record a full movie of a molecule, what could we use it for? Just to name, a few examples that could come to mind. If we could understand photosynthesis not only globally, but really on the atomic level, if we could see what happens, this may lead to technology that could make much more efficient use of solar energy, for example. Or remember this cure of the Ebola virus, which somehow seemed to cure people, but nobody really understood why or how it worked. If we could watch viruses in action, like temporarily, then this may enable us to design specific targeted drugs, because to understand how they function, you really need to be able to visualize the underlying dynamics, not only their structure.
Where do you know your photoelectron spectra from?
So we record it. We actually record them spatially resolved.
But you get a signal, and how can you identify where the signal is from? Let's say you mentioned
Because you use a specific atom in that molecule, one specific one, and you can deduce from the energy from which level and which atom the electron has come from.